Hey guys, so this is the last bit that we didn't get through in class. We left with me telling you guys about the Ames room and giving you the next slide that showed you the picture. Really, for the Ames room, it's important that you understand that what's being manipulated in here is going to be monocular depth cues, that they're going to deal with things like relative size, relative height, even things like linear perspective. And the alterations that they make, as long as you're going from a certain vantage point, makes it look like a squared up room. But reality is that it's actually a slanted trapezoidal room. But as long as you manipulate enough of the factors, it looks squared off. And again, it's from a very specific vantage point. Here again, you have the idea that because everything seems standard, really the picture that is on the right seems to be the best version of this. Those are all three adult men of the exact same height. And because one of them is pushed closer and the one that's on the left side of the room is further away, the one that looks closer looks taller, looks bigger. It's bigger on our retina, but everything else stays in proportion. The doors to the left and the right side are in proportion. The two windows look to be the exact same. Nothing really seems off. The one that's up higher in our field of vision versus the one that's lower in our field of vision, well, because of the tilt of the floor, relative height gets kind of becomes obsolete. Because there are no grids on the floor, we're not really looking so much at the idea of linear perspective, but you can still see how the walls seem to track back and they come back to a single vantage point and they seem parallel. So the entire point of the Ames room is that we make these assumptions based off of these monocular depth cues and they can be flawed. If you're interested, this is a clip that goes into force perspectives in movies, specifically Peter Jackson talking about force perspective in his filming of Lord of the Rings. The last couple things that we need to talk about, we'll talk about perceived motion and then we'll talk about constancies. Perceived motion, there's two kinds that you need to know. There's stroboscopic, and then there's also the phi phenomenon. The phi phenomenon we've seen before. The amazing lights, or if you guys remember, I flashed up on the board a bunch of red dots, and it looked like there was a green dot that was traveling around in a circle, especially if you looked at the center. And what you were getting was the green after image of the red dot. But really, the only thing that was truly happening was the turning on and off of lights. Nothing more, nothing less. But your brain put that into motion. And so you got this kind of sensation that that light was traveling around because of the blinking on and off of the lights. Stroboscopic motion. Stroboscopic movement is what you utilize when you're looking at art or when you're looking at movies. This is still images being presented at a very fast rate that gives you the perception of motion. Now, another easy way of looking at this is flip books. So if you've ever created a flip book, a stack of paper, and you put like a stick figure on it and the stick figure does a cartwheel or something, it's a static image, but because it is a rapidly changing static image, you get it, or you get the motion. Another one, if you read Captain Underpants, I believe that's a correct book that my son reads, and there was Fliporama, literally two different images on a page and you just kept flipping back and forth, back and forth, back and forth, and it looked like the image moved. I think you guys might be young enough to remember Captain Underpants. I hope. Here is a really good example of what we'd call the phi phenomenon. Now, you should hopefully feel like Christopher Walken is kind of floating towards you. He's not. This literally is the switching of the background and his image from black to white and black to white, and you get this sensation that he's moving. It is, again, the phi phenomenon. This is not two different pictures switching back and forth. It's the same image, but the light is going from black to white, on, off, on, off. Last thing that we needed to get through, perceptual constancies. I've talked to you guys about these a couple of times, but again, you just need to know the three major ones. Color or lightness constancy. In other words, we assume that things don't change color. It's really just the amount of light that's being reflected off the object that we perceive. So, strangely enough, greater light source, the object is a different color, but we realize that no matter how much we manipulate our light sources, the colors always come back. Whatever was red still continues to be red. Whatever was green continues to be green, so on and so forth. So color is constant. When we look at shape constancy, I always use the example of a door. If you were squared up to the door, it looks like a rectangle. You open it a little bit, it looks like a trapezoid, but you still in your head understand that the shape has not changed, and so on and so forth. And it's because we've manipulated objects to understand that we can guess, or there's a certain reasonableness about what the shape would be. So that door, we open, we close, we see it at a different angle, we know it's a rectangle. Size constancy has to do with the changing image on your retina. Something far away has a small retinal image, something close up, large retinal image. We use that as an indication of motion. We assume that the person who is 5'6" and all the way down at the other end of the hallway will still be 5'6" when they're right up next to us, even though on our retina they look like they're maybe about 1 or 2 inches tall. So size stays constant, shape stays constant, color or lightness stays constant. This is just another really kind of neat way of how we can see how monocular depth cues can violate constancies. As the object moves further down the hallway, it's moving up in your field of vision, so relative height is being manipulated. The lines are tracking back to a focal point, so you have linear perspective that's giving you a certain amount of information. And the size is staying constant. What we know because of size constancy is that as the object moves further away, it should feel or get smaller. Since it stays the same size, we see it as growing. And that's because it's violating the relative size law that we have for our monocular depth cues. Here you have the Ponzo illusion again off to the right-hand side. And using those two red images, both of those rectangles are exactly the same size. But again, because we have those two lines going to a vanishing point in the background, the one at the top has to be larger visually because it is being able to almost touch both sides of the parallel lines. That means the one in front must be smaller. It also seems to be thicker or wider. And again, that has to do with the idea that it's higher in our field of vision, so relative height. But if they're the same size and there's one that's further back, it must be far larger because of relative size. The two monsters in the picture to the left, exact same size. So all of these monocular depth cues are helping us understand what should be further away. And here you can even look at things like, and actually both of them, you can look at things like texture gradient. The asphalt close up has a lot of texture. Further away, texture starts to kind of diminish. Here, the bricks have a bit more texture or detail. They become less detailed and textured as you move away. All of those things set up the illusion, even though the monsters are the same size, the two red lines are the same size. Every single one of the elephants is the same size, and again, you can just go in relative size, relative height, linear perspective, texture gradient, all of those things are being manipulated, and that alters how we perceive the object. These guys are all the same height, and again, it's the same things that are being violated. And this kind of gives you a little insight into how the Ames room works, because here you're seeing them travel up. In the Ames room, you wouldn't have this idea of the sloping up. So before I told you a little bit about brightness constancy or color constancy. Now, it's the idea that we perceive color to be unchanging regardless of the type of illumination. There's one little thing that can actually alter what we would consider brightness constancy, and that's if you alter the background. When we look at the comparison or the contrast between a light background and that purple disc and a dark background in the purple disc, we start to see the purple disc as being a different color because of the contrast of the background. This is a pretty good example of how the background can actually affect color constancy. Not so much with the green pants, but if you are looking at the shirt, those shirts are actually the same color. In fact, the entire person in each of these photos is using the exact same color scheme. It's just the background that seems to be different. And again, with the dark background, the shirt appears to be a much lighter gray. Put a lighter background and the shirt appears to be a much darker gray. And that is just one of the manipulations that we have with kind of brightness. So if the background is unchanging, we assume color to be unchanging. We assume that brightness is going to be consistent or constant.